In the previous video, we have learned about how to use the Riemann sum to approximate the area under the curve. Okay, and then we have also used the sigma notation to express the Riemann sum. As you can see from this illustration, we approximate the area under the curve here fx by divided into n number of equal rectangles, and the Riemann expression, the right Riemann expression for this equal to sigma from n equal to 1 until n fxi delta x, where delta x equal to b minus a divided by n. So how can we link this Riemann sum into the concept of definite integral? So I'm going to draw again this graph. Okay, so more or less look at that, and let's say this is the x equal to a, and this is x equal to b. So to closely approximate the area under the curve, I will need to subdivide the area with more number of rectangles. Let's say then we have a delta x here. Delta x is very small. Okay, delta x is very small. It's close to 0. So we can have this is the first rectangle, second one, the third one, the fourth one, and so on and so forth. Okay, then basically we can make the delta x which equal to b minus a over n become very small, close to 0. The way to do it is that by making n, so the number of rectangles, as many as possible. So the way to the notation for this one is to make n approaching infinity. Okay, so when n approaching infinity, delta x will be close to 0. So how can we include this notation in the Riemann sum? So in Riemann sum, we have sum of n equal to 1 until n fxi delta x. Okay, so we can include the limit here for limit, okay, and approaching infinity, and this expression is actually similar to the definite integral of from a into b fx dx. In this case, dx is infinitesimally small, very small. Okay, so how can we prove this one? We can prove that one by actually doing some trial and errors. For example, here, let's say we are asked to find the area under the graph of fx equal to 1 over 5x squared between x equal 2 and x equals 6. So according to the definite integral concept, the solution for this one is quite simple. So it's integral from 2 to 6, in this case 2 is a, 6 is b, of 1/5 x squared dx. Okay, so the first way to approach this one is we can make a simple Riemann approximation by, for example, do the R4. So n equal to 4. So we divided the area under the rectangle into 4 equal subdivision of rectangles. Of course, from this illustration, we can see that actually whatever we get will overestimate. Okay, because by splitting into 4, you can see that an extra area. Actually, this is above the above the curve. So basically, if you use 4 Riemanns, 4 equal rectangles, you will result in overestimation of the actual area. And actually we can do a lot of simulation, a lot of trials, and then as we increase the number of n, for example here, when r equal to 1, okay, we have the first approximate area is 28.6, but as we increase the number of rectangles, for example here we have for r equal to 13 we have about 14, and then when we increase to the number of rectangles to 48, it's 14.13, and if we increase further with r equal to 100, it's 13.66. So actually the more number of rectangles we divided the area under the curve, the closer it is to the actual area. So what if we could take the Riemann sum for this one? Okay, we take Riemann sums with infinite equal subdivision, a lot of it. So in that case, okay, we can set n is equal to infinite, but of course we cannot do n equal to infinite, but we can approximate the infinity by using the concept of limit you have learned in the beginning of this module. So we can use a notation of limit and approaching infinity of Riemann sums. Okay, so this is the fact, quite important fact actually. So if we really do all of those things, okay, we actually will find out that it is actually equal to the integral of 2 to 6 1/5 of x squared dx. Okay, and then it doesn't matter whether you use a right Riemann sums, a left Riemann sum, or any kind of common approximation like trapezoid, something we've learned earlier. It will end up with the same, which is integral from 2 to 6 1/5 of x squared dx. So let's do it. So how can we form the Riemann sum for the infinite, for this function, infinite number of the n? So the basic steps are the same as the one we discussed earlier. So first we define the delta x that we set as a constant, the width of any rectangles, okay, and then we also set xi, which is the x value of the right edge of the each rectangle. So in this case we use right Riemann sums, and then we define fxi, which is the height of each rectangle. Okay, what can we do then? Here we define delta x, which is b minus a divided by n. In this case we have 6 minus 2 divided by n equal to 4 of n, and xi is equal to actually here equal to a plus if you remember earlier delta x times I. So we end up with, because the a equal to 2, it's 2 plus 4 over n I, and fxi we define, so we just substitute xi in this function, okay, and we know what is the we substitute xi to this function, then we will get if fxi equal to 1/5 of xi square, and then we substitute this xi with this guy over there. Okay, then we can define the area of the each rectangle, which is equal to delta x times fxi, right? Okay, and we use the Riemann sums, okay, for defining the area, and we'll end up with this term, and we can then represent the actual area as the limit. So limit and approaching infinity for Riemann sums then equal to this term.